here at Motek, here in Amsterdam. I think we have about 80 people joining at the moment. I would like to thank you all. We know that there's participants here from all over the world, so we're very excited about that. First off, before we start the webinar, I would like to go through some of the practicalities first. So today we'll be doing a 1-hour session. The first 45 minutes of the session will be a presentation by Professor Dr. Vander Bogart. After the presentation, we will do questions and answers. You can post your questions through the GoToWebinar tool. As you can see on the right-hand side, you can just type in a question. My colleague Johannes Gijsbergs will gather all the questions, and after the presentation, we will discuss them with Professor Vander Bogart. Also, during the session, we'll be doing a couple of audience questions. These will present to you on the screen. This will be just a multiple choice question for us to get some input from the audience. Okay, so these were the practicalities, the technical part. Now I would like to give a short background on why we're doing this webinar. Today's webinar is about the human body model, or HBM. HBM is a real-time biomechanical musculoskeletal model, and HBM is a very important part of the Motek solutions, in which it is used for clinical gait analysis, gait retraining, and other feedback applications. HBM was originally launched in 2008 in a collaboration between Motek and Professor Vander Bogart. But earlier this year, we released a major update of the model, and therefore we thought it was appropriate to do a webinar session. This model was developed in an EU-funded project within the 7th framework. It's called the Model-Driven Pediatric Digital Repository, or MD Pedigree. And in this project, Motek collaborated with clinical gait specialists from the Department of Rehabilitation Medicine at the VU Medical Center, with the Rehabilitation Hospital Pellenberg in Leuven, and one of the technology partners was the Delft University of Technology. And throughout the whole project, Professor Vander Bogart remained a consultant for the development of this new and improved model. Therefore, it's a great honor for us that Professor Vander Bogart is here with us today to do this webinar session. Just to give some background on Professor Vander Bogart. He was originally trained as a physicist and mathematician. He has studied everything from computer-aided movement analysis to sports medicine. In his current work, he is revolutionizing robotics, and he always has a great interest in the mechanics of motion. He currently holds the Parker-Hannifin Endowed Chair in Human Motion and Control in the Department of Mechanical Engineering at Cleveland State University in the US. And Professor Vander Bogart has a long-lasting history of collaborating with many companies. And he's also the brain and the developer behind the first version of the human body model. So again, it's a great pleasure for us that he's here with us today to present and discuss the HBM model. Of course, he's not here in Amsterdam, he's in Cleveland. So we're now going to give over the control to Professor Vander Bogart. So bear with us for this technical transfer.
Good. Welcome. I'm Ton Vander Bogart. I'm here in Cleveland, and I'm very happy to have this opportunity to present to you. I believe you can all see my screen now. So thank you, Flores, for the introduction, and thank you to Motek Medical for this opportunity. You've heard a little bit about me in the introduction, but for me it would be helpful to know also a little bit about the technical background of the audience. So we have a little poll that we want to do at the very beginning here, and that should pop up on your screen in a few seconds, and then you can answer the questions. Let's see. So the purpose of this poll is that I know a little bit about your technical background, and so if you can click on these buttons, then in a few seconds we should be able to see the result. This is very good. So I see that a lot of people have quite a bit of experience in using software for movement analysis and musculoskeletal modeling. Especially 58% wrote their own code. So very high technical level of expertise, I think. So let's continue. What we're going to do today, I'll talk a little bit about the history and the motivation of the human body model. I'll describe the model in a little bit of detail, and then the methods of analysis that we're using. Also, I'm comparing HBM to OpenSim in the capabilities and then also in the results that we get from both systems. Then I'll talk about the applications that you can use to interact with the human body model, a little video with a demonstration, and finally future directions where I'll ask for your input again. And then we'll have 15 minutes available for questions and answers, and you can type your questions in the chat window at any time, and they will be collected, and we will answer selected questions at the end. So first of all, thanks to Oshri Evan-Zohar, who is one of the founders of Motek, and he had the idea to do this development. And I've also enjoyed very good collaboration with the software developers at Motek, starting with Thomas Geitenbeek in 2007, and more recently Ben and Johannes. There was a very important clinical input for the development of the HBM2, especially Jaap Harlaar and Marjolein van der Krocht. And when I'm showing the comparison between HBM and OpenSim, that was work that is done by Antoine Vallice at the University of Leuven in Belgium. So just a brief history. Around 15 years ago, Motek had developed this system called CAREN, which stands for Computer-Aided Rehabilitation Environment. And it consisted of a motion platform with force plates. It had real-time motion capture, and it had a system for real-time data processing and visualization. And that was all combined into a virtual reality system. So the reason for the motion capture was that they wanted the virtual reality to be able to respond to the motion of the patient, and also so you could produce an animation of the patient, an avatar on the screen in real time. So because you already have the force plates and the motion capture, you might ask the question, well, why don't we do the motion analysis? And that's exactly what Oshri suggested in 2006. But to make it useful in virtual reality, it has to be done in real time, which means the analysis has to happen at the same time that the data is collected. So what is state-of-the-art motion analysis? That's kinematics, kinetics, and also estimating muscle forces. So there are very important reasons why you might want to do real-time movement analysis. Well, first of all, clinical movement analysis is already well established for about 25 years. And it can be used to diagnose certain conditions and to evaluate the treatments, monitor progress. So typically that's done in an offline analysis where you collect the data and then you do analysis and you generate a report within a few hours or maybe a few days. If you could do this in real time, which means you do the analysis at the same time as the person is performing the test, that report can be printed as soon as the person comes out of the Gait lab. You can also give the patient feedback while they're still doing the test, and that's a Gait retraining sort of environment where you try to give feedback so the patient can improve their gait. And also this information is available to the therapist during the test. So the therapist can do things like, well, try walking this way, and then they can immediately see if the joint moments or muscle forces have improved. And then finally, you can use these biomechanical variables such as forces and angles and torques to control a virtual reality application. And that picture is one example of that, where you see a bar graph displayed on the ankle joint, and then green would mean that you have a good push-off, and red would mean that it's not enough. And you can also score points. You see here score 27. So you can program this virtual world to respond to biomechanical variables. So the history is that in 2007 was when we were first successful in making this work. It was available to customers in 2008 in the D-Flow environment, which I will talk about later. There was a patent in 2011, and in 2013 we published a technical paper, which you should look up if you're interested in more of the technical details. It is open access, so you don't need a subscription, and there are a few online supplements with it, with the full details of the model and the computational methods, and then also it has Excel files with results from subjects that are walking. And then, as mentioned before, there is a 2.0 version released this year. So the original goals, as specified, were that we needed to be able to do a full human body model, so legs, arms, trunk, head. It had to be three-dimensional, and we need to produce kinematic analysis, joint angles, and kinetic analysis, joint moments, and also estimate muscle forces. And to be useful for real-time and virtual reality, you need to have an update rate of something like 25 times per second. So this flowchart gives you an idea of the data flow. So on the left side we have the inputs. So we have real-time motion capture, and that's, at this point, it's camera-based, marker-based motion capture, and then force plates, and that goes into kinematic analysis first. Then we have some filtering and differentiation. Then we do inverse dynamics, and then finally static optimization to solve the muscle forces. And then besides muscle forces, we have joint moments, joint angles, and also muscle length changes coming out of the analysis. And I'll talk more in detail about these components. Okay, I'll present the model in a little bit of detail. So the full body model has 44 kinematic degrees of freedom, and they are sketched over here. So first of all, 6 degrees of freedom for the pelvis, motion, translation, rotation relative to the ground. Then we have 6 degrees of freedom in each leg. 3 in the spine. There are 2 joints in the spine, one just above the pelvis and one between the lumbar spine and the thorax. And the 3 rotations are distributed between those 2 joints. Then 3 in the neck, and then shoulder has 6 degrees of freedom. There's no scapula, and then 4 degrees of freedom in each arm. And what we do is, when you use the human body model for a specific patient, all these bone lengths and the alignments of all these joints are determined for that specific subject. There's also a smaller version, which we call Gait plus Trunk. It has 15 degrees of freedom, and basically the arms and the head have been removed. That allows you to use a smaller marker set, and if you're only interested in the legs and the trunk, then this is more appropriate. And then there's an even simpler one that's called Gait, where we have just the pelvis and the legs, and that's an even smaller marker set. So that makes it more practical if you're only doing gait analysis. So again, these bone lengths and joint centers and joint axes are determined for each subject, and here's a few examples of how that's done. So first of all, we have I'm going to do this for the full body. So the full body marker set looks like this, and there are 32 so-called anatomical markers that define where the joints are, and that's done while the subject is standing. So we get the coordinates of all these markers, and then we calculate where the joints are. And then there are additional markers on the body that are just used to track the skeleton motion. And for having a robust kinematic analysis, even when markers get hidden, Sometimes we have a redundant marker set, and typically the full body marker set is 47 markers. Robustness is very important in real time because you cannot do any editing of the data before you do the analysis. Skeleton definition is done for one joint at a time, and I'll just talk a little bit about the leg here. So the hip and the knee are critical. So we have, for the hip and the knee, we have two options. So you can define the hip joint center based on the pelvis markers, and that's done with a method that was published by Harrington. So you get the coordinates of the markers on the pelvis, and you calculate where that hip center is. But we can also do a functional joint center, which is you ask the patient to do a range of motion test, and then the kinematic center of rotation is determined. And there's a similar option for the knee where you use either the markers or a functional joint axis. For all the other joints, it's only based on markers. And a few examples of that. So for the ankle, we put the ankle joint center right in between the two markers, and the axis goes through the markers as well. And then we drop down a certain distance, and then we get the center of the subtalar joint, and then in the subtalar joint we draw a line that's 42 degrees inclined from a line through these two markers. And then in the horizontal plane there is a 23 degrees, and that's all based on a very old anatomical study published in 1969. In the trunk we have these two joints that I mentioned earlier. The joint just above the pelvis, and then the joint between the lumbar spine and the thorax, and they're determined from markers. Let's talk a little bit about the kinematic analysis. So we have 44 kinematic variables. We can define a vector called Q that contains all these variables, and then the inverse kinematics problem is an optimization problem where you want to find values for all these 44 variables such that you minimize this function, and this function is a sum of differences, and it's the difference between where the mocap system saw the marker and where the model says the marker should have been if it was in that particular position. And if you can find the minimum of that function, then you get the model to match the markers as well as you can. OpenSim uses exactly the same inverse kinematics approach, and you'll find that same equation in the OpenSim documentation. There are different methods of solving these optimization problem, and we use a Levenberg-Marquardt method coded in C, which is very, very fast. And we can do that in about 1 millisecond for the 44 degrees of freedom. The next step in the processing is a low-pass filtering and differentiation step. We use a second-order Butterworth filter, which is standard in human movement analysis. And it's not very well known, but a second-order Butterworth filter can actually be modeled as a differential equation, a second-order differential equation, which you see in the box here, where x is the input and y is the output of the filter. And there's one parameter, which is the cutoff frequency. So we take the ground reaction forces and the kinematic variables, and then we run that through this filter, which we simulate in real time, and then we get the filtered kinematics, and we also get the first and the second derivative, which we're going to need for the dynamic analysis. So that is the output of that filter. Typically, we use a cutoff frequency of 6 Hertz for gait, but that is you can set that in the user interface. You can choose your own cutoff frequency. If you use 6 Hertz, you get this amplitude response, which is exactly the second-order Butterworth filter. What is important, what you don't normally have in offline analysis, is this time lag. In offline analysis, we use a zero lag filter, but you can't do that in real time because zero lag requires data from the future. So we always have a little bit of a time lag, and it's about 40 milliseconds when you use a 6 Hertz cutoff. So it's not much, but you have to be aware of it. The inverse dynamic analysis will require that we have mass properties for all the body segments, and we use equations that were published by De Leva in 1996. That gives us the body segment mass, the center of mass, and moments of inertia. And they're calculated from the total body mass and the bone lengths. And the bone lengths we already have in the kinematic model. There are equations that are different for males and females. So I've written the equations of motion here in the form that are normally used for robotics, where on the left-hand side you see generalized forces, and on the right-hand side you see terms originating from inertia, Coriolis effects, gravity, and then the measured forces. So everything on the right-hand side is known, and we measure 12 ground reaction force variables. We have a force and a moment in 3D on one leg, and a force and a moment in 3D on the other leg. So we can compute that right-hand side in about 0.4 milliseconds, which is good. And then we get all these generalized forces, and I've split them into two parts. The first 6 are the forces and moments that move the pelvis relative to the ground. And we know that there isn't really any muscles or motors between those two body segments. So we know that these need to be close to 0, and that's why we call them residuals. And that's only the case if you have the full body model, then all the mass is accounted for. So it's a good idea to inspect these and make sure that they're close to 0 if you do have the full body model, and you can do that in the user interface. The other ones are the joint torques, and so those are the torques that really create the motion. So now we have our joint moments. The next step is the muscle analysis. So in the full body model, we have 300 muscle elements, and they come from various sources. So the lower extremity muscle models come from Delp's work that was published in 1990, and there are 43 in each leg. Then there are 102 shoulder and arm muscles, and that comes from a paper published by Chadwick in 2009. And then the trunk muscles come from work from Lambrecht. So all of these models, they were available in OpenSim, and we do some pre-processing to speed up the computation. So first of all, we export from OpenSim a large database of moment arms at various positions of the skeleton. And then we fit polynomials to the data. And those polynomials give us an equation to very quickly calculate the muscle length from the joint angles Q. And it's a number of terms, and each term has a coefficient C. And so those coefficients are obtained from that database. And then once you have that polynomial, you can also very quickly calculate the moment arms because they are the partial derivatives of that polynomial. So we've already done that pre-processing, and all those polynomials are stored in the HBM configuration file, so you don't have to do that. So with these muscle models, we do static optimization. So we have our joint moments, and it's actually 38 because the first 6 are not joint moments. And then we have a matrix that contains all the moment arms, and most of those are actually 0 because each muscle typically only goes across 1 or 2 joints. But for instance, the hamstrings, they would cross the hip and the knee, and the hip has 3 degrees of freedom, the knee has 1, so there will be 4 moment arms for the hamstrings, right? Then the static optimization problem is to find the muscle forces that minimize this particular cost function. So we take the sum of the squares of the relative muscle forces. So each muscle force is divided by the maximum strength of that muscle, multiplied by the volume, and then added up over all muscles. And that accomplishes the load sharing. Then we have constraints. Each muscle force has to be positive because muscles can only pull, they can't push. And then if we multiply the muscle forces by the moment arms and add them up, they have to produce the joint moments that we already know. and that is a system of linear equations. There's the matrix D multiplied by this vector of muscle forces, and it has to be equal to those joint torques. If you use the upper extremity model, there's also inequality constraints, and that's also a set of linear equations. And that basically says that we only accept solutions that would not cause the shoulder joint to dislocate, and that's a condition on the muscle forces. And that's necessary to make sure that the rotator cuff does its job in preventing the shoulder from dislocating. And that's based on work from Vander in 1994. So the static optimization problem is a quadratic programming problem, as we wrote it on the previous page. And that's because the cost function is quadratic and the constraints are all linear. The standard methods for solving those problems are not very suitable for real time, because you don't know if you're going to have enough time to go through all the iterations, and if you don't have enough time, you end up with nothing. Fortunately, there is a method based on a recurrent neural network that was published in 2005. A recurrent neural network is a neural network where the outputs get fed back into the inputs, and there are also integrators in there. Basically what this is a large system of differential equations. And the inputs would be the joint moments, and the outputs would be the muscle forces. This is a very big neural network because we have 38 joint moments and we have 300 muscle forces coming out. But computers are fast, and you can solve this recurrent neural network in real time. And the good thing about this method is that if you run out of time, because the next piece of data is about to arrive, then you can just stop the solution and it will be an approximation. You end up with something that's a good approximation. And we found that you can get within about 1% of the actual solution in about 5 milliseconds. So putting all these things together, now we have the whole data flow, and measuring the computation speed, we can do the inverse kinematics in about 1 millisecond. Filter and differentiation is very fast. Inverse dynamics is also very fast. And then we use a fixed amount of time for that static optimization. And then altogether, we're doing this in about 7 milliseconds. So we can process well over 100 frames per second with this. So much better than what we had hoped for, which was 25 frames per second. And finally, how do you interact with this? So dflow is Motek's application environment. So dflow is a data flow programming language where you have modules and you can have data flow from one module to the next. And dflow also then provides the real-time control for your treadmill, your motion base, and your visualization on the screen. So HBM is a plugin in dflow, and it's located inside the mocap module, which you see over here. The user interface is one tab inside the mocap module. You see that on the right here, and there are just a few things you need to enter, which is the gender of your subject, and then if you don't have medial markers, you have to enter the width of the knee and ankle, marker diameter, and then when your subject is standing in the standard position, you click on calibrate subject at the bottom here, and the model is created at that instant. And then outputs that come out of the HBM that are available in dflow are joint angles, moment, and power. And then for the muscles, we have length change and muscle force. So what you're going to see next is a video with a demonstration where a person is walking on the treadmill. We're using the Gait plus trunk model, so not the full body. Streaming data will come in from 26 markers and 2 force plates. And then the outputs will be shown in 2 different ways. The muscle forces are visualized as color on the graphics of the human model, and then we also see a graph of the knee angle. And so I'm going to start the video. They will pop up in about 5 to 10 seconds. And what you'll see is you'll start with an empty D-flow application, and the application is created as you are watching this video. So I'll wait a few seconds until the video is there. And I'm going to start the video. Okay, so first the mocap module is dragged onto the screen. There's the data stream is going to be turned on, and it comes from a file here, not from real data. It just comes from recorded data, but it acts exactly like real data here. So we're going to see on the left side of the video, you will see the raw data. So there are the markers. Person is standing here. And we'll start walking now. The model has been, I'm not sure if the model has been initialized yet. We will see that in a second. So we're going to the HBM tab. Okay, the person is standing again. Now the model is going to be turned on by enable HBM. It's not initialized yet. Female. And then the calibrate subject button at the bottom is clicked. And now at this time, you will see the model be connected to the markers. And now the real-time solution is actually running. And we'll see muscle forces visualized as colors. There you go. You'll see some green. That means the muscles are active. And now what you will see is some real-time graphing. Okay, first, yeah, let's look at the outputs. So here we'll see muscle outputs, and we'll see joint outputs, angle, moment, and power, just to see what all is available. We have muscles, joints, we have center of mass, we have intersegmental loads for the knee. Okay, now we're getting a graph module on the screen, and we're drawing a line from the mocap module to the graph. So there's data coming out of the mocap module into the graph module, and there is a knee flexion angle is going to be plotted as the first channel on that graph. And here you'll see a familiar knee flexion angle graph. And then the green one is the knee joint moment graph. So that's how easy it is to use the HBM in real time and get real-time information out. I will go back to the PowerPoint here. Okay. And so you can make these D-flow applications very fancy if you want to give your patient real-time feedback in a virtual reality environment. So here's an example of a more sophisticated D-flow application where you have graphics to show you, in this case, a forest. And then on the right side, you'll see some examples of visualizing mechanical variables on top of a simple avatar. So here we have knee flexion extension, pelvic tilt. So if you wanted to train somebody to improve their pelvic tilt, you could visualize it and have them watch that while they're walking. This is the example that I've shown you before, the ankle push-off application. So this is a real-time feedback to help the patient improve their ankle power at push-off. And it turns out they can actually improve by this sort of application. So I'll show another video here. There we go. So here you'll see what that looks like. So that cylinder that's drawn on top of the ankle on the right side, it will show red, yellow, and green, and then the blue bar is actually how strong you did your push-off. And when the blue bar reaches up into the green, you know you're doing well. When it's in the red, you're not pushing hard enough. And so this gives people some encouragement to do well. And each time you do well, you score a point. So you can turn this into a game and make the training very effective. Go back to my screen here. Then for offline processing, there's another application called GOAT, the Gait Offline Analysis tool. I'm not going to show the video, but this is what that looks like on your computer screen if you run it. On the left side, there are graphs with familiar gait variables, angles, moments as a function of gait cycle. Here is a video that was recorded during the session. And then here is the HBM visualization. And this is all synchronized. So you can go interactively through your recording, and you see something happen in the graph. You can say, well, what was the person doing at that time, and what were the muscles doing at that time? So you can explore and come up with interpretations of your gait data. So this is a tool that we think is useful for clinicians. And then you can export your gait analysis report, these gait graphs, as a PDF, and you can also export the numbers on a CSV file and process it in Excel or MATLAB or whatever you like. I want to say a few things about comparing HBM to OpenSim. So starting with the bad news, so HBM, you do not get the source code, and you do have to pay for using it. So OpenSim is open source and you don't have to pay. They have a lot of the same capabilities: inverse kinematics, inverse dynamics. HBM has this model built in. It has some options, but basically you're stuck with this model that we created. In OpenSim, you can use any model. You can create your own model, but most people tend to use this same gait model that's available with the OpenSim software distribution. So as you've seen, we generate this model from marker data while the person is standing, and you can do a functional hip-knee center if you want. In OpenSim, the process is a little bit different. The models are typically already built without any motion capture data, and then they are scaled to the subject. You don't get a functional hip knee center, although you could probably program your own if you wanted to. Both can do static optimization. They have some different options, but basically they have the same basic capabilities there. HBM is strictly an inverse analysis, so it processes data. OpenSim can also be used for simulation, so HBM is not a simulation tool. HBM is real-time, so we process streaming data, and if you do offline processing, it's very, very fast. OpenSim is strictly post-processing, although there was a recent paper by Claudio Pizzolato who showed how you can do real-time kinematics and kinetics with OpenSim using the C++ programming interface. It was a lot of work to develop that, and he had to use multiple processing cores, and there's no muscle analysis there, but it's definitely something that may eventually be possible. This is the main thing for me, I think. HBM is very easy to use, as you saw. OpenSim tends to be hard to use, and that's not surprising. It's a very powerful system. You can do anything with it, so there is quite a bit of a learning curve to use it effectively. HBM is robust. It has to be, because it's real time. If something goes wrong with the data, it has to keep working. OpenSim is not as robust, is not real time, so you may end up having to do some editing on the data to get everything to work correctly. HBM comes with applications with a very nice user interface for movement analysis. You can program your own applications in dflow, which is a very easy to use programming system. OpenSim comes with the graphical user interface, but it's fairly minimal. The graphics isn't as nice, and you can make some graphs, but it's definitely not a clinical gait analysis tool. If you wanted to create more customized tools, you could program that in MATLAB or C++, but it's going to be a little harder than using dflow and Goat. Results between HBM and OpenSim, and this was done by Antoine Vallis. He used both systems with exactly the same input data, so same motion capture and force plate data. And hopefully that paper will be published in Journal of Applied Biomechanics. Results are very similar except for the subtalar joint angle, and that's because there is a very different subtalar joint orientation in the two models. Then you can ask the question, well, which kinematic model is actually better? And for that, we look at the residuals in the inverse kinematic analysis. And that comes out to about 6.5 millimeters for the OpenSim model and 4.7 millimeters for HBM. So it's not a huge difference, but it could mean that that subtalar joint model in HBM is better than the one in OpenSim. And this was the Gait 2392 model in OpenSim. The joint moments are also very similar, except for the subtalar joint moment, which is very different, and a little bit of difference in the peak of the sagittal plane knee moment, and that can come because that OpenSim model has a moving knee axis, and we have a fixed knee axis in HBM. Muscle forces are also quite similar if you use the same cost function for the static optimization, except for the psoas, which I don't really understand why that is. The peroneus I can understand because that subtalar joint moment was very different. So HBM gives you a peak in the peroneus force at the end of the stance phase, and OpenSim gives you basically nothing. And you look up EMG of the peroneus longus, you do see that peak at the end of the stance phase. So again, that's a clue that our subtalar joint angle in the joint axis in HBM might be better. I would like to end with a little bit of discussion about future directions, and there's so many things you can do now for the HBM 3.0, which may be another few years. And some of these are easy, and some of these require a lot of research and development. So it's important to know what the priorities are of the community. So we're going to do a little poll in a minute, but let me go through those options. So I've always advocated for having a MATLAB interface so that you could program your MATLAB scripts and do analysis that way. For my needs, the Goat and dflow don't really satisfy that need. I like to be able to write scripts that produce figures that I can put in an article, and especially I think for students that would be nice. And so especially be nice if that would be inexpensive or even free. And Motek is considering that, and that may actually come soon. One thing that I think a lot of people might wonder about is, well, can we make our own models in HBM or import a model that we've already developed in OpenSim? And right now that's not possible, but if that is a high priority, that could be done with some effort in the development. There is also work on developing subject-specific models from MRI, so where you actually determine your joints and even your muscle paths and muscle properties from MRI data for a specific subject. And if there's a strong interest in that, and then that could be developed as well. Then we can also go to more, I would say, less expensive laboratory environment, or maybe even outside the laboratory, where we want to do things without force plates. Or instead of camera-based motion capture, we may want to use inertial measurement units or something like Kinect. That would require a lot of research because we don't even know how good that would be if you tried that. And so these 5 we're going to have in the poll, so you can vote on those. And other things we can do that are not that complicated, I guess, is we can try to use alternative cost functions in the static optimization, so more options there. and we could try to use muscle dynamics, so hill models instead of just static models. So let's get that poll on the screen. I see it on my screen now. So we're going to ask you for your first priority and your second priority. So first vote on the first one. Okay, let's see if we can get some results. This is great. The MATLAB API and student version have great interest, so I'm happy to see that. Maybe I advertise it a little bit too much. Let's look at the second one. That'll be interesting as well. So that should be one of the others. And it looks like there's a strong interest in other motion capture technologies. And that's very good to know. And then the second place there would be the user-defined models. So this is very useful information for us, and we will definitely process that and use that in deciding what the priorities are. So what we're going to do next is questions and answers. So if you haven't already done so, you can type your questions in the chat tool, and then questions will be selected, and then I will answer those selected questions. And also, you will receive an email at some point with links to the recording of this webinar and also links to some other sources that might be interesting.
Okay, thank you, Ton Vander Bogart, for this presentation. We have some questions. We have about 10 minutes left, so hopefully we can go through them. If anybody has any additional questions, please let us know. So the first question was, can we allow additional outputs for the HBM model, like contact forces and let me see, segment orientation, joint direction forces, and joint contact forces. Do you have a comment on that? So
segment orientations, they definitely are available internally, so that would be fairly simple to make those available in the outputs of the mocap module. That would be fairly simple. Joint contact forces is a little more complicated, and that's because we do the analysis with generalized forces, so we only get the torques that contribute to the motion. We don't get the reaction loads. Now we do have an extra bit of processing to do that for the knee. There was a lot of interest in getting things like anterior posterior force in the knee and valgus moment and that sort of thing. So we have that, but that is a intersegmental load. That is not a joint contact force. So to get the joint contact force, you would have to include the muscle forces in the analysis, and then you have to know the orientation of the muscle forces, and we are not computing that for you. So if we had a model that was identical to an OpenSim model, and I've done that in other projects, you could actually export these muscle forces and these motions in a text file, then import them back into OpenSim, and then OpenSim can calculate all those reaction forces for you. But right now, HBM doesn't do that for you.
Okay. Thank you for that. So we have another question: is why are we not using the 3 degrees of freedom in the knee joint?
That's a very good question. So the other two rotations, they tend to be small, and to get reliable angles for those other two rotations, you have to worry about the skin motion artifact. You probably need more markers. But the main reason is that those rotations, those other two rotations, are not controlled by muscles. And the main philosophy behind the HBM is it is a tool for analysis of muscle functions. Not so much for the details of the joint moment, or joint motion, which is more orthopedics related. I would say we're a little bit more on the rehabilitation and neurological disorders on that side of the spectrum. If you really want to look at detailed joint motions, I always feel like that's very hard to do with a full body model. Then you need to do a study where you put lots of markers on the thigh and lots of markers on the shank, and you do a really good study on knee motion. That's a different type of work.
Yeah. Okay, thank you. Yeah, so we have the question: what are the main differences between HBM1 and HBM2?
Mostly to make the HBM more in line with the clinical protocols and the clinical applications. So for instance, in the HBM1, we assumed that the person could be standing in a neutral position. And then we would construct the joint axes. Some of the joint axes were assumed to be in the medial-lateral direction of the global coordinate system. Well, if you have a cerebral palsy patient, they may not be able to stand in a neutral position where you can make that assumption. So in HBM2, the joint axes are now no longer dependent on how the patient is standing, which is very important for clinical applications. And then there were some improvements in how the joints are defined. So for instance, we used Bell's method for the hip joint in HBM1, and now we use Harrington's method, which is more recent. So it's mainly to kind of update it to the more recent knowledge and to clinical applications.
Okay, so thank you. So we have a question here about HBM reflects an able body. How are you expected to use in treatment with patients with physical and neurological impairments?
So if you have impairments, then this whole static optimization may not be applicable anymore. Because the static optimization assumes that the muscles distribute the load in an optimal way. Well, if you have a muscle that is either hyperactive or it's weak, then that muscle will either contribute more or less to the joint torques. So I think static optimization, you have to be very careful about applying that. The muscle forces that you get out of here, they are based on that assumption of an optimal distribution of load. So you have to be very careful with static optimization. And so maybe in the future we need to start considering a sort of EMG-informed analysis where you use the joint moments, but you also use EMG to help you figure out that load distribution. And that would be more suitable for patients with neurological disorders. Okay,
so does this also hold true for the kinematics and the kinetics? Or
no, those ones you don't have to worry about because that's just mechanical analysis. Those ones are fine.
Okay. So we have the question here: can HBM be used for non-gait tasks, for example, reaching?
Yes, there's no reason why you couldn't do that. Postural control experiments or reaching experiments. I don't know how many people have used the upper extremity. when we use the full body model, sometimes we get the arms being twisted in a weird way, and then we have to reinitialize the HBM. So it's maybe not quite as strong in the upper extremity because it hasn't been used that much for that sort of application. But if anybody's interested in doing that, I'm sure that Motek would be interested in supporting that and learning from your experience.
So the question here is, how is the ground contact modeled?
There is no ground contact model. We just take force plate data.
Okay, quick answer. Let me see. So we have a question here. So most models are based on direct kinematics. HBM uses inverse kinematics. Can you comment on why you made this choice?
There are a few reasons. So the first one is that inverse kinematics is much more robust if you have a real-time situation and markers might drop out unexpectedly, and you still need to get a solution. You don't want this, HBM to just pop up a window that says, "Sorry, I don't have enough markers." So with inverse kinematics, you get a high level of redundancy. We can probably have about 10 markers drop out before the kinematic analysis will fail. The other reason is that we're using a model for the inverse dynamics and for the muscle function, and it's a model in the style of robotics. So we have generalized coordinates, we have generalized forces that are responsible for the motion, and it makes sense then to do the kinematics only with those variables. That way we don't have joints coming apart, because with the direct kinematics you always have that risk. And then I can think of a third reason, and that's the animation. So when you do animation with direct kinematics and you transfer the direct kinematics results to a graphics model and you have it walking on your screen, it will look quite bad because some joints might come apart, the feet might come away from the ground, the feet might be squishy. This is a well-known problem in the computer graphics world, and inverse kinematics will eliminate all of those problems.
Okay, so thank you for that final answer, because we're running out of time here. So we've gone through many of the questions. The questions that are still open, we will come back to them offline, so in the further communication. So I'd like to close this webinar session. I would like to thank you very much, Professor Vander Bogart, for doing this presentation. I hope the audience had some very interesting insights from you. And we would like to thank the attendees for joining us today. Like we said, the webinar will be shared afterwards for future reference. If you have any additional questions later on, please contact us, and we will gladly help you out. Okay, thank you very much, Tom.
Thank you for your attention, and goodbye.
Okay, goodbye.